In this unit, we are going to look at a reaction known as Williamson ether synthesis, which is a way to take alcohol starting materials and through a couple of steps of reaction, ultimately convert them into ether products, such as the diethyl ether that we see in the lower right-hand corner there. And just as a reminder, when we're talking about ethers, the functional group we're looking at is an oxygen that's single bonded to two carbon atoms. And those carbons cannot be carbonyl carbons, or this would be another functional group such as an ester, but instead bonded to just two standard sp3 carbon atoms right there. So in order to do the Williamson ether synthesis, what we are going to first do is convert our alcohol molecule into a better nucleophile. So in order to convert the alcohol molecule into a better nucleophile, what we need to keep in mind to convert the alcohol into a better nucleophile is that anionic nucleophiles are generally superior, stronger in other words, to nucleophiles that are neutral. So in the alcohol we have a neutral oxygen. We'd really like to make that oxygen anion. And one way to do that is by reacting the alcohol with sodium or potassium metal, because that will convert that into an oxygen anion. So the reaction for this is the product of this reaction of an alcohol with sodium or alternatively potassium metal is going to be an alkoxide anion with the corresponding cation, so a sodium cation or potassium cation. And here in this molecule, the portion that we're interested in is generally going to be the alkoxide anion, with the metal cation simply acting as a spectator in subsequent reactions. So we refer to this oxygen negatively charged that's bonded to the alkyl group as an alkoxide, due to the oxygen and the alkyl group there and the fact that it's negatively charged. So we can take that alkoxide anion and we can use that as a very good capable nucleophile. And that's what we're going to do in the Williamson ether synthesis portion of this reaction, is we will use that alkoxide anion as a nucleophile to attack a primary alkyl halide carbon that's bonded to that good leaving group, the halogen leaving group, to force the formation of a new oxygen carbon bond. So after we've converted our alcohol group into a better nucleophile, that is the anionic alkoxide, then second, what we're going to do is the portion of this reaction that is the Williamson ether synthesis itself. So the Williamson ether synthesis is going to take that alkoxide anion that we just generated, and we will react it with ideally a non-sterically hindered alkyl halide. So an alkyl halide is going to certainly have a good leaving group onto it. I'm putting alkyl chloride there, but there's certainly other options. This will allow an SN2 type reaction to take place. And again, it's worth noting and keeping in mind here and writing down that this has to be a non-sterically hindered alkyl halide. So we take that oxygen anion, bring that over, form a covalent bond to the carbon that's bonded to the leaving group as the leaving group leaves. So this should look like a very typical SN2 reaction. It has the special name Williamson ether synthesis because of the discoverer of this reaction being named Williamson. So R, our alkyl group, oxygen, and then our new carbon-oxygen bond in blue bonded to our R prime alkyl group to finish off the ether. And then we'd also generate chloride anion as a result of this reaction. Ethers tend to be very stable products. They undergo very few reactions other than combustion. And so this product that we make here, the ether product, would be expected to be a very stable product. So on this page, we've looked at generalities of taking alcohol molecules, converting them into alkoxides by reacting them with metals, and then using that alkoxide anion as our nucleophile to execute a Williamson ether synthesis by attacking an electrophilic R prime group here, an electrophilic carbon as the leaving group leaves in an SN2 type process. Now that we've looked at this generally, let's go into a specific example and I'll give you a chance to work through this example problem. So let's predict the product of the reaction of isopropyl alcohol, first with potassium K, and then secondly with 1-chloropropane. So isopropyl alcohol, we need to remember how to draw the structure of that. So it's going to be our isopropyl group directly bonded to our alcohol group. When we treat that with metal, be it potassium or sodium, what's going to happen is that we are going to get rid of the hydrogen atom, creating an oxygen anion, so O-, and we'll have potassium there as our counter ion for that. Then what we will do is take that oxygen anion, is going to be very nucleophilic. We mix it with our primary carbon of 1-chloropropane. So we'll go ahead and draw out the structure of 1-chloropropane. That's going to be the perfect situation for an SN2 type reaction to take place because our carbon that's bonded to the leaving group here is going to be very positively polarized. So what happens is the oxygen anion comes in, attacks this carbon that's bonded to the leaving group as the leaving group breaks away like so, and that's going to give us our product of this reaction, that is the ether product. So we'll have shown in blue here what originated from our nucleophile, and then I'm going to show the newly formed bond in green, like so, and then in black, the 3-carbon chain, 1, 2, 3, that originated from right here. So carbon 1, carbon 2, and carbon 3, or carbon 1, carbon 2, and carbon 3. Make sure you don't put any extra carbon atoms in, always double check. So I need to erase a carbon atom there to give us our final ether product of this Williamson ether synthesis. A quick warning about Williamson ether synthesis: it is going to work best at non-sterically hindered alkyl halides. So if we are trying to do ether synthesis and our target ether molecule is asymmetrically substituted, meaning that the oxygen atom of the ether is bonded to both, say, a primary and a secondary carbon or a secondary and a tertiary carbon, you want to design the Williamson ether synthesis accordingly. So say our target molecule is this. We could envision two different strategies for synthesizing that from an alkoxide anion and an alkyl halide. So thinking about combinations of alkyl halides plus alkoxide anions that we could use to enable the synthesis of this, the two strategies as we dissect the molecule are that we could think of taking either the oxygen atom plus this part of the molecule and making that the anion that comes in and attacks the other portion of the molecule, or alternatively, we could instead think about using this molecule as an anion and attacking the carbon atom here, which would be bonded to our leaving group. So to write out these two possible scenarios, the two possible ways of doing this, we could take our alkyl halide, which would be tert butyl chloride, and react it with ethoxide anion, like so. Or alternatively, another way to do this would be take and place our oxygen atom here to give us tert butyl oxide, reacted with ethyl chloride or ethyl bromide, whatever you want to do, in a Williamson ether synthesis. One of these two ways would work really well. The other way would not work well at all. So the way that would not work is going to be the way on the left, where we have a tertiary alkyl halide, because what's going to happen here is that there's going to be too much steric hindrance for the oxygen anion to come in and do an SN2 type reaction. So the oxygen anion is going to be trying to come in here and attack, but it's not going to be able to do that because of the fact that there's too much bulk around that tertiary carbon. And so therefore, this approach is not going to work very well at all. Instead, what would generally happen would be that alkoxide anion would act as a base to do an E2 elimination reaction on that carbon instead. On the other hand, if we have the situation here on the right, where we have a non-sterically hindered carbon bonded to the leaving group, a primary carbon, in other words, bonded to the leaving group, then what's going to happen is that the oxygen atom of our nucleophile is very nicely going to be able to come in, attack the electrophilic carbon as the leaving group leaves, and give us excellent yield of our final desired product. So the warning here to take heed about is that when you're thinking about designing Williamson ether syntheses, you want to make sure to pair a alkoxide of a variety of different structures that can be relatively flexible or variable, but you want to make sure that the alkyl halide has a primary carbon bonded to the leaving group, because otherwise, if it's secondary or tertiary, you're going to start picking up a lot of steric hindrance, and that's going to make the reaction very difficult or impossible to achieve. And you can run into some situations where there simply won't be a way to make a compound via Williamson ether synthesis. So we could ask, which of the following compounds could not be synthesized using Williamson ether synthesis? So looking at these 4 compounds, I'm going to mark them as checkmark or X to indicate whether they could be synthesized by Williamson or whether they probably won't be able to be synthesized by Williamson. So taking a look at the upper left-hand corner here, we take a look at the carbons that are directly bonded to the oxygen. Ask yourself whether either of those 2 carbons are a primary carbon, because we need one of those 2 to be a primary carbon in order to enable us to set up the reaction so that we have an alkyl halide that's a primary alkyl halide and is therefore not too sterically hindered to be attacked by the oxygen anion. So in this case, neither of these 2 carbon atoms that I put in red here are primary carbons, and so therefore this could not be synthesized in good yield by Williamson ether. So I'm going to put an X on it. Coming over to the diethyl ether, here and here, both of those are primary carbons, and so therefore this would be an excellent candidate to synthesize by Williamson ether synthesis. So I'm going to put a green check mark on that to indicate that it can be synthesized by Williamson ether synthesis. We come over to the next situation. We have a secondary carbon there that I just put the red dot on. Over here is a primary carbon. As long as one of the 2 carbons is a primary carbon, we will be able to do Williamson ether synthesis because we'll be able to set it up so that this carbon is the carbon that's bonded to the leaving group. We want to make sure the primary carbon is the one bonded to a leaving group to get this reaction to work out. We come down here to the bottom. This is a secondary carbon right there, so that's not going to be a good place to put the alkyl halide halogen in our starting material. But if we come over to here, that is a primary carbon, so this would be an excellent situation to do a Williamson ether synthesis.